Okay, so this is my presentation um, for intelligence agents for week three. Again, just gonna go over what I learned this week, what I did different. So I tried creating diagrams to help myself better learn. So back propagation. So as we learned last week or the week before in week two, gradient descent wants to minimize the average error of the cost function. And the reason why we want to do that is because we want to adjust the model's parameters such as the weight and biases. This is what helps us minimize, so like adjusting these weights or biases minimizes the average error. And we want to find the negative gradient because negative gradient finds the minimum point or the local minimum and which decreases the error. So the problem with this is that as we saw in the last lecture, in a 3D plane, it's quite easy to visualize. We just travel down the hill. However, in a dimension of like 13,000 dimensions, it's quite difficult to do that or envision that. So there exists an algorithm to solve this. It's called back propagation. And right now I'm going to go to the intuition behind it. So the example I'll be talking about is focusing on the Henry digit number two and having a neural network that's not trained. So what we want to do is just adjust or nudge the activation in certain directions. And then the size of these nudges should be proportion to how far away it is from the current value. So this is an example that diagram I made. So as you can see, this is just for one example of a neuron within a layer. This one labeled two, and the layer before it is the previous layer, with each of these activation points pointing towards two. So the three ways to increase a neuron's activation, as you can see, the three things we can manipulate are number one, the weights, which are indicated by the red lines, the activation values, which you can see on these neurons right here with the purple value label, and the biases. So these are three things we can manipulate to increase a particular type of neuron's activation. So there's a theory, the Hebbian theory, which basically summarizes is neurons that fire together, write together. So what this is trying to say is that if a neuron is activated from previous neurons, then those neurons are most likely to activate the neurons that it thinks it should activate. So the largest increases to weight um, comes from the neurons that are most active. So what the algorithm wants to become more active. The neurons firing when seeing a 2 get more strongly linked to those that are thinking about firing when thinking about a 2. So I kind of reinstated that last slide. Um, so the first thing we can adjust are the weights. So the way we want to adjust weights is um, by it's depending on the what's it called again, the activation value. So if the activation value is high or is high, these weights will have more of an impact if adjusted on the the forward activation value. So for example, on the left side with the highlighted weights, right, the highlighted connections, if the activation point was higher, then I'm the weights in have a bigger impact on the determining the activation. So the other thing that we can also manipulate is activation changes. So the values within the neurons from the preceding layer. So as you can see, the changes with activation should be proportional to the weights. So the higher it goes, the the more impacts what it's originally doing. So for example, this first neuron on the left, if its values is super high, um, or we can say bright, adjusting that activation value to be higher will make it brighter. And that goes vice versa for dim. So the values that are really low with low activation, we can think of them as really like dim. So making the activation value less will make it more dimmer. So the intuition or the conclusion to this intuition is that each neuron has its own desires about what should happen in the preceding layer. And in this diagram, I took a screenshot because I didn't. It's too complicated to draw this all out. But basically, in this previous the previous slides on how we adjust it, it goes for each neuron value within a layer. So um, what the propagation does, it takes these activations within each of these layers, so these desires, and combines it to take account the corresponding weights and how much each neuron needs to change. So this recursively goes. So for example, we active for this layer on the right, we take those desires and then it propagates backwards, which will take the desires previously to that until it gets to, I guess, like the beginning. So you could think of it like as a recursive approach. It keeps doing this iteratively, recursively, and the process is then to relevant weights and biases that determine those values, repeating the same process and moving backwards through the network. By adding all these together, you get a list of nudges what you want to happen, and repeating the same process and moving backwards to the network. This is where the idea of propagating comes from. So stochastic gradient descent. So basically, if you were to do this, the true gradient for like calculating each of these desires, when if I go back here, if we were to do this each individually, the computer would take more than, I believe mentioned in the video, 100,000 years or more. It just very long in general. So it takes it takes computers a very long time to add up the influence of every training example. So what scientists have done is that they randomly shuffle these test datas, right? And when they shuffle it, they make it into a list of mini batches, and they compute each step of those mini batches, and they give a pretty good approximation on um, how to minimize the cost error or find the gradient descent. You could think of it like um, in the previous um, video, we had the gradient descent calculated every optimized step to go down to find the local minimum, right? So you could think of that person calculating each step, slowly going down, and the way that stochastic gradient works is kind of like a drunk guy stumbling aimlessly down. He's still going to fall to the bottom and reach that local minimum, but it's more of a messy kind of way. And I have these two images right here: Rock Lee using Drunken Fist versus like Light Yagami, who is very like quick and calculating of his every step. So language learning models, I'm just gonna basically go over what I learned from what I'm understanding. So language learning models weren't always like the way it used to be, the way it predicted words. It used to predict words line by line until I believe it was Google that came out with a thing called transformers. So what transformers does is that it takes each word and assigns a vector value to each of those words, and those words will talk to each other, or at least pay attention to the context of the words around it to determine what the next word should be, or to predict what the next word should be. For example, if I were to say riverbank versus Bank of America, we can determine those two different banks. So like riverbank is referring to like a platform on a river, versus Bank of America is an actual bank that you can go get money from, deposit money and such things. So that's what transformers have done. And large language models, like over umbrellas that umbrella transformers. So the way large language models predict stuff is that it um, basically, it's like from the example in the video, it was tuning each of its predictions on what should be best fit. So like it comes up with a list of predictions and the probability of those predictions, whichever is the highest, it will pick. So that's what I learned from large language models basically. And to train them is to gather like a bunch of text throughout the internet and basically learn from that. So yeah, this is what I learned last week. Thank you for watching, and I'll see you.